Hey, Algebra 1. I was looking at your multiplying polynomials lessons, and they do cover some special cases, so I thought I would go into that. Also, they cover degree of polynomials. I know that was in the first lesson, but I think it's a good time to actually go ahead and take a look at that. So I'm going to share my screen with you guys so we can take a look at some of those things. First of all, we'll talk about the classification of the polynomials by degree. So you guys are pretty aware of monomial, binomial, trinomial, but the main thing that they're tricking you with would be the degree, and the degree is the highest exponent. So that's easy, except for the ones. So like in this example here with the 10x squared minus 7x plus 5, the highest exponent's obviously 2, so the degree is 2. It's called a quadratic equation. Degree 2. But then when you look at the one right below it here, you have multiple variables within each term. So it's still a trinomial. However, the degree, it looks like the highest exponent's 3, but there's actually a variable combination here linking the a with the b. And the exponent rule with multiplication is that you technically add the exponents, even though you can't add these exponents because they're not like bases. To find the degree, you would technically take the degree of the a, which is a 1 right here, and the degree of the b, which is 3, and add it together. So the degree of this trinomial is actually a 4th degree polynomial. So, and that's higher than any of the other terms in this polynomial expression as well. So you got to watch out. For example, here we did these on pinch cards in class. The highest degree in this problem, you always look at the front thinking that's going to be your degree. However, this time it's actually over here at the end. The highest degree is a 4. The example here in number 5 I have, which is I think most typically like the ones that they're tricking you with. You have this trinomial, and you look at the first one and you think, oh, well, even if you know the rule and you would add the exponent here, the 3 plus the 1, and make it a degree of 4, you actually have a higher degree term here. So you got to watch out with all the terms, especially when you have multiple variables and especially when they're mixed up. So the degree of number 5 here in this example is actually a degree of, pop it out. And if you said 6, you're right. So trying to inject a little bit of my old school flair when you're in the class. You probably remember the pop it out. So hopefully that was enjoyable. The next thing I want to talk about would be, your multiplying special patterns here. So these examples, we would have done these in class when we were factoring, but I just want to look at them from the standpoint that they are, classified as either a difference of squares or a perfect square trinomial. So let me move my mug out of the way over here. This will work. So the difference of squares has to follow the a squared minus b squared pattern. So that goes over here. A perfect square trinomial has to follow the fact that it's got a trinomial, so 3 terms, and the first term and the last terms are perfect squares. The middle term, we always said, just kind of works out in most cases that it's 2 times the square root of a and b. So I'm going to move both of these over here because I'm definitely looking at a perfect square trinomial. The a and the b at the end are both squares. And I'm going to move this one which way? Difference or perfect square trinomials? Get it up top, don't say, ready, pop it out. Difference squares. All right, hopefully you did that. And this one right here, we're gonna go, which way? Get it up top, don't say, ready, pop it out. Perfect square trinomial, yeah. All right, so I'm being a goofball. Anyhow, these two, you would GCF first, and if you GCF'd, I bet it would go over here. And this one, since it's a trinomial, and it's on this slide, and you took out a GCF, I bet it would go over here. So now that we've categorized them by difference of squares or perfect square trinomial, let's look at their factorization. So let's see if we can get this to focus here. For x squared minus 9, we need 2 numbers that multiply together to get us -9, but then they're also going to add up to nothing because the middle term, remember, it's x squared plus something x plus a c term right here, right, where we had a b and a c. And whatever we could use here, we had to find two numbers that multiplied and then added up to b. So here we need a positive and a negative to get a -9. And we need them to add up to nothing. So essentially we need it to be its square root. So 3 and -3. So when you're looking at the multiplication problems, if you see two groups, two binomial factors that are almost exactly the same, but the only thing that's different is their sign. You're looking at a difference of squares. The next one there is 36x squared minus 121. And the square root of 36x squared, get it up top, don't say. Ready? Pop it out. 6x. All right, I hope you said it. And it's a -121, and they need to add up to 0, but they also have to multiply to get negative. So I need a plus and a minus. And what's the square root of 121? Get it up top, don't say. Ready? 11. All right. And if you were to take this and multiply it back out, you're going to get all 4 terms, but those 2 terms in the middle are going to cancel out. Okay, so let's switch sides and let's go look at the perfect square trinomials. Move my ugly mug over here. And we'll start out with the x squared plus 22x. And now we're going to factor this the exact same way, knowing that we need to split up the x squared into x and x. We need 2 numbers that multiply together to get the number 121, and it's a positive. So I know that my choices could be plus plus, or to get a positive, I could also multiply 2 negatives. So I might also have a negative in here. The indication as to why I picked plus plus is because it's a positive 22 right there. So I'm going to use the 2 numbers that multiply to get 121 and also add up to 22, which would both be 11 and 11. And now you notice the difference between this example, which they are both exactly the same, and then the examples of the difference of squares above, that they are very close to the same, but they're differing by a sign. So when you multiply these out, the middle term would add up to nothing. It'd be like a plus 3x and a minus 3x when you multiply it all the way out. And the same thing here, you'd have a negative 66x and a positive 66x, which would be null and void. They'd cancel out. Here you'd get a positive 11x and another positive 11x, which would add up to a positive 22x when you multiply it all the way out. I can do the exact same problem, keeping the 121 positive, but then making the 22 negative, as in the example over here on the screen. The only difference for that is going to be the signs. We're still going to need the x and the x and the 11s. But now this time we're going to have to get a negative and a negative, because I still can get a positive 121. I can still get that positive 121 when I multiply. But a negative 11x plus a negative 11x would equal negative 22. So that is a perfect square trinomial. So you can see that these are exactly the same, and these are almost the same, but they differ by a sign. So what do you do with the 4x squared plus 28x plus 49? Well, the 4 and the 49 are both perfect squares, and it's a trinomial. So we're assuming and hopeful to get that 28x in the middle by using the square roots in our factorization. So we'll use 2x and 2x to get 4x squared. Again, the square root of 4 is 2. 49, the square root of that is what? Get it up top, don't say it. Ready? Did you say it? Pop it out? 7. And now you can see that with the positive 7s, we'll get 49. But if I were to multiply this out, I would at some point multiply that and get 14x, and that and get another 14x, which would indeed add up to the 28x that we need in the middle. So if this was a minus 28 right here, then we'd have to change it to 2x minus 7 and 2x minus 7. You're probably going to see these written as 2x plus 7 squared or 2x minus 7 squared. Whereas up top here with the difference of squares, you can't rewrite these like that because they're not the same. So hopefully this helps you with some of the special patterns and the degree stuff with exponents. If you have any other questions, hit me up on email and we'll Zoom later.